What if I told you that the algorithm powering the most hyped AI models right now has a fatal flaw? A mathematical bug so fundamental that NVIDIA researchers just published a paper exposing it. Today, we're going to present Group Reward-Decoupled Normalization Policy Optimization. That's a mouthful, so we call it GDPO. It's a multi-objective reinforcement learning improvement over Group Relative Policy Optimization, or GRPO for short. The training algorithm introduced by DeepSeek R1 last year and used in dozens of other reasoning models everyone's been excited about. In the following slides, we'll break down exactly why GDPO works, where GRPO fails something the authors call advantage collapse, and how a simple fix makes your models stop ignoring safety and formatting constraints. Let's dive in. Beneath the hype of reasoning models lies a difficult balancing act. We no longer train for just correctness. Real-world deployment requires a tug-of-war between conflicting objectives. Now, quick context. When training large language models for tasks where we don't have a nice differentiable loss function, we use reinforcement learning from human feedback. Humans annotate by hand some harder datasets by adding a score to them. If the score is high, the large language model adds a high signal to loss. If the score is low, the large language model penalizes the loss. This way, the large language model can learn a hard task, like write a joke that doesn't make you cringe, or explain Bitcoin to your grandmother. But here's the problem. What happens when you're learning multiple objectives at once? How do you train one model to be ethical and to be funny and to know math and to write poetry when these goals actively pull the loss in different directions? That's exactly what multi-reward reinforcement learning tries to solve. And that's where group relative policy optimization start to break in ways nobody expected. Let me walk you through exactly how the standard approach works. This is Group Relative Policy Optimization, and it's what DeepSeek R1 introduced last year, and everyone has used for reasoning models. Group Relative Policy Optimization follows a simple two-step logic. Step 1 is aggregate. You take all your individual reward scores, correctness, format, length, and you simply add them together into a single number. RSum equals R correctness plus R format plus R length. Simple addition. Step 2 is normalize. This is where you calculate the advantage, your actual training signal. It tells the model which responses were better than average. You take that single reward sum, subtract the mean across all responses in your group, divide by the standard deviation. Classic Z-score normalization. But here's the trap. It looks logical, right? Sum first, then normalize. But this sum first approach and then normalize destroys the signal from individual data objectives before the model ever sees it. Let me show you exactly how. Now let's see exactly why summing first is a trap. This is the core insight of the entire paper. Imagine your model generates response A. It's beautifully formatted, clean JSON, proper structure, every bracket in place. But the actual answer inside, completely wrong. So the format reward gives it a perfect 1. The accuracy reward gives it 0. Add them together, total sum equals 1. Now for response B, it's a mess. No structure, ignores all formatting rules, just raw text. But buried in that chaos is the correct answer. Format reward 0. Accuracy reward 1. Add them together, total sum also equals 1. Here's the problem. When group relative policy optimization normalizes these sums to calculate the advantage, the actual gradient signal, both responses, get the exact same value. To group relative policy optimization, these are mathematically indistinguishable. The algorithm literally cannot tell the difference between correct answer, bad format, and wrong answer, good format. This is called advantage collapse. The model receives identical training signals for opposite failure modes. It's like trying to teach someone the difference between left and right, but every time you say left and every time you say right, they hear the exact same word. Learning becomes impossible. Let me show you this information destruction visually. We ran a simple experiment, 2 binary rewards, 2 model responses per question. On the left, GRPO. Look at all these input combinations flowing into the system. 0-0 means both responses failed everything. 1-0 means the first response got 1 point, second got 0. 2-1 means first response got 2 points total, second got 1, and so on. Each of these represents a meaningfully different situation. The model behaved differently in each case. But now watch what GRPO does. All these different inputs get squeezed through this information bottleneck, and everything collapses into just two output groups. Advantage Group A and Advantage Group B. That's it. 9 different input scenarios, 2 output signals. We just destroyed more than half our training information. Now compare GDPO on the right. Same inputs flowing in. But instead of a bottleneck, we have signal preservation. The output? 3 distinct advantage levels: high, medium, and low. GDPO correctly recognizes that a 2-0 pair where one response completely dominated deserves a stronger training signal than a 1-0 pair where the difference was smaller. GRPO throws away this nuance. GDPO preserves it. And that preserved information is exactly what lets the model learn which behaviors to reinforce. Now for the solution. And honestly, the elegance of this fix is beautiful in its simplicity. Introducing Group Reward-Decoupled Normalization Policy Optimization. And the name tells you exactly what it does. It decouples the normalization. Step 1. Decouple and normalize. Instead of summing all rewards first, we normalize each reward completely independently. Look at this formula. A 1, the advantage for reward 1 equals R1 minus mean 1 divided by standard deviation 1. What does this mean in plain English? Take the first reward value, subtract the average of that reward across all responses in your group. Divide by how spread out those values are. AN does the exact same thing for reward N. Every single reward gets its own independent normalization, its own mean, its own standard deviation, completely separate calculations. This is the key insight. We calculate a separate normalized advantage for each reward component. Format reward gets normalized on its own scale. Accuracy reward gets normalized on its own scale. They never mix until the final step. Step 2. Aggregate. Only after normalizing separately do we add them together. A sum equals A1 plus A2 plus ... plus AN. And here's why this matters. By decoupling, a formatting failure and a reasoning failure remain distinct errors in the gradient. The model can learn from both separately. No more collapse, no more confusion. Now, decoupling introduces a new problem, and if we don't address it, training can fail completely. Here's the issue. When you normalize each reward separately and then add them together, the magnitude of your final signal grows with every objective you add. Think about it. One normalized reward ranges from roughly -1 to +1. Add a second normalized reward, now your sum ranges from -2 to +2. Add 5 rewards, -5 to +5. 10 rewards, the range keeps growing. This inconsistency destabilizes your gradients. The optimizer doesn't know what scale to expect. So here's the complete GDPO pipeline. Follow the flow with me. Input rewards come in on the left. They pass through decoupled normalization, each reward normalized independently, just like we discussed. Then summation combines them together. But before that becomes your output signal, there's one more step: batch-wise normalization. This is the final stabilization layer. It takes whatever sum you have, whether it came from 2 rewards or 20 rewards, and normalizes it one more time across the entire batch. Now your output signal is always on a consistent scale. Look at what happens without this step. The orange line GDPO without batch normalization flatlines near 0, complete training failure. The model learned nothing. The green line full GDPO with batch normalization climbs steadily past 1000 on the correctness reward. Stable, successful training. 2 components. Decoupled normalization preserves your signal, batch normalization stabilizes it. You need both. Enough theory. Let's look at real results. This is the tool calling task using Qwen 2.5 instruct. Graph 1, correctness score over 1500 training steps. GDPO in green launches upward immediately. By step 200, it's already at 0.8. By step 500, it's past 0.9. and it stays there, stable, consistent, nearly perfect accuracy. GRPO in red, slow climb, plateaus around 0.3 at step 500, eventually crawls up to 0.6 by the end. That's a 40% gap in final performance. See this arrow? GDPO superiority, that gap between the green and red lines? That's not noise, that's not cherry-picked data. That's the difference between an algorithm that preserves information and one that destroys it. Graph 2. Format score. Can the model output valid tool calls in the correct format? GDPO shoots up to nearly 1.0 within the first 100 steps and stays there. Perfect formatting every single time. GRPO struggles to break 0.4. Noisy, inconsistent. By the end, it's still only around 0.35. The model simply cannot learn proper formatting with GRPO. Key takeaway: GDPO achieves higher scores in both objectives simultaneously. There is no compromise, no trade-off. Better accuracy and better formatting. That's what happens when you fix the math. Remember that disaster we just saw? GRPO collapsing, abandoning accuracy, violating its own length constraint? Now let's run the exact same experiment. Same model, DeepSeek R1, 1.5 billion parameters, same competing objectives, but this time with GDPO. Graph 1, length reward. Both methods shown now. Green is GDPO, red is GRPO. Both achieve high-length compliance early on, but look at the difference in stability. GRPO in red is noisy, erratic, jumping around. GDPO in green stays rock solid at the top, consistent, controlled. Graph 2, correctness reward. This is where GDPO shines. Remember how GRPO collapsed after step 300? Watch the green line instead. Resilience. While GRPO's red line crashes down toward 0, GDPO's green line keeps climbing. 0.3, 0.4, 0.5, past 0.6. It just keeps going up. Same model, same data, same competing objectives. Completely different outcome. Graph 3, maximum response length. The smoking gun from before. GRPO in red. Response length explodes past 300 tokens. Total loss of control. GDPO in green, control. Response length stays flat around 50 tokens throughout training. The model maintains discipline. GDPO forces the model to do the hard work of being concise and correct. No shortcuts, no collapse, no reward hacking, just stable, successful training on competing objectives. Let's look at the scoreboard for the 3 tested domains. Domain 1, Math, the AMI benchmark. Competition level math problems. GRPO length violation rate 91.5%. That's a fail. The model violates length constraints more than 9 times out of 10. GDPO length violation rate 10.8%. Success. That's an 80 percentage point improvement. 80% fewer violations. Domain 2, coding, apps and code contests benchmarks. Look at the bug ratio. GRPO, that long red bar, produces significantly more bugs in its generated code. GDPO, that shorter green bar, lower bug ratio. Cleaner code, fewer errors, more reliable outputs. Domain 3, tool calling, GRPO format, correctness, decent but not great. That red bar stops short. GDPO format, correctness, plus 4% improvement over GRPO. That green bar extends further. Nearly perfect format compliance. Read that banner at the bottom. GDPO wins on real-world tasks, not just toy problems. This is NVIDIA research. Production-grade validation. 3 different domains. Math, coding, tool use. Same result every time. GDPO dominates. The evidence is clear. The algorithm works. Let me bring everything together. The problem. GRPO sums rewards before normalizing. This causes advantage collapse. What does that mean in practice? Distinct behaviors look identical to your training algorithm. A model that gives correct answers but bad formatting. Same training signal as a model that gives wrong answers but good formatting. The algorithm cannot tell the difference. Learning becomes impossible. The solution. GDPO decouples normalization to preserve signal fidelity. Normalize each reward independently first, then sum. Then apply batch normalization for stability. That simple reordering, normalize then sum instead of sum then normalize, fixes the fatal flaw. The proof. Superior convergence across all benchmarks, greater stability when rewards actively compete, predictable linear control when you adjust weights. The evidence is overwhelming. Read this carefully. GDPO isn't just an alternative, it is the necessary new baseline. If you're training models with multiple objectives, GDPO should be your default starting point. Have you experienced these training collapse issues with GRPO? Are you going to try GDPO on your next run? Let me know in the comments. I genuinely want to hear how it goes. If this breakdown helped you understand multi-reward RL better, hit that like button and subscribe. I break down cutting-edge AI research papers every week so you can stay ahead of the curve. Thanks for watching. I'll see you in the next one.